So my name is Olivier. I work at a company called L Acoustics. And at L Acoustics, we build sound systems. So we've been doing this for almost 40 years. We're French, so I think you can probably hear. And when I say we build sound systems, so this includes speakers, the amplifiers, and nowadays those systems are very, very complex, so there's a lot of software going on. So this is our Sound Vision, which is an acoustic prediction software, which is used by our customers to predict how the speakers are going to cover the audience area before preparing a show. The amplifiers are networked. They have DSP embedded in them, so this needs to be controlled. So that's our network manager software that they use. And for the past 10 years, we've been diving into this world of spatial audio for live sound. And the team in London, that's what we do. And we call this ELISA. And here you have an example of a deployment across the stage. So you see 5 hangs of speakers instead of your traditional left-right stereo setup. And the processing for this is powered by what we call the ELISA processor. And this can do 128 inputs times 128 outputs at 96 kilohertz sampling rate, 3 milliseconds round-trip latency. And so all the examples you're going to see are going to be about the software that runs on this platform. So this platform is a PC-based platform. It runs an Intel chip with Linux running on it. And if most of you are developing plugins targeting macOS and Windows maybe, I think you're going to be jealous of Linux because it gives you amazing ways of controlling performance and scheduling and also looking at what's happening under the hood. So because I'm also here to give some awareness about object-based audio and spatial audio, I'll just very quickly remind you of those concepts. So for object-based mixing in spatial audio, we use the concept of audio object. So an audio object is basically the combination of 2 things, a mono audio channel and some positioning metadata. So in our case, we have an azimuth, so a pan, elevation, because we can pan in 3D, a distance, so how far this object is supposed to sound from the listener's perspective. And we can also talk about width or size of the object. And so we define all of this in a software called ELISA controller. And then we have our ELISA processor. So the ELISA processor receives the audio inputs, typically from a mixing desk, the metadata from our UI, and then we get spatial audio out of this. And we can also receive metadata from external control sources like mixing desks or plugins, but that's basically the idea. Okay, so we're not going to talk about real-time systems, just to make sure we're on the same page about what we're talking here. So in a real-time system, correctness depends on, obviously, the output being correct. This, I think, we can all agree with. Also, the execution time needs to be within that threshold. If you're under that threshold, you're good. If you're over, it's failure of the system. So not meeting a deadline is system failure. And so for audio systems, that means basically we need to process or synthesize or record. Actually, that's also an interesting use case that we don't talk about this much in this conference. 1 block of audio in less than the time it takes to play back this block of audio. So I'm sure you're all familiar with this concept. So if we look at the real-time computing platforms that are available to us to build products, and I will place them on this scale of the most real-time friendly to the least real-time friendly. So the most real-time friendly is analog electronics. You don't need to care about anything. The speed of your system is dictated by wave propagation, and unless you're building analog systems across the scale of a planet, you probably don't care about latency. The next step is discrete digital electronics. So if you think of the first digital reverbs in the 80s, that's how they were built. It's actually quite hard to make sure you're going to meet your deadline because you need to look at the specifications of all your chips, the frequency they can run at, and when you get close to the limit, you might enter subtle bugs. And the natural evolution of digital discrete electronics is digital electronics on a single chip. So either programmable chips like FPGAs or application-specific integrated circuits. I've put them more on the right because they're more complex, but actually to guarantee correct execution, they're easier to use because your silicon vendor or your FPGA vendor will give you tools to analyze the critical path in your circuit, and it will tell you if it's running, if it will be able to run at the frequency you want it to run at or not. And then on the second line, that's when we introduce software. And we're all software developers, or I think at least most of us. And software is a pain because it's an abstraction, so it allows us to be a lot more expressive when building products, but also this abstraction gets in the way and we're not really sure how it works and we're not sure what's happening on the actual chip. So the first step will be what we call DSPs, so digital signal processors. You would typically program them in some kind of flavor of C. They don't run an operating system, but it's still software. They're usually very good at processing a large number of floating point numbers in little time. They have accelerators for the typical operations we might want to do for signal processing. So an example is the Shark DSP. That's what L-Acoustics uses in our amplifier. We also use FPGAs. And then the last really red actually is your maxed out MacBook. I haven't put a Windows machine, which in my opinion is even worse because Microsoft doesn't give you APIs as good as Apple to control real-time constraints. But basically what we're going to talk about later is how to take a PC, right? So Intel ARM architecture with an operating system and try to make it a little bit more real-time friendly. So how to real-timeify your Penguin. And so we're going to talk about two aspects of this, about things that the kernel does and how to use what the kernel gives you and what you need to do also at your application level. So just to recap, when you're writing audio code, I'm sure all of you know that. So real-time audio programming 101, no memory allocations, no syscalls, no locks or mutexes, no I/O. Well, that's also syscall anyways. Just plain good DSP, your audio thread should be just doing math, basically, and all will be good. Will it? So let's talk a little bit about memory, because we say no memory allocation, because a memory allocation could block, and usually that's where people stop in the talk. So I want to use this also as an opportunity maybe to talk about some of the things I've learned into this journey and talk a little bit more about how operating systems manage memory. I will talk about schedulers. So all of this also applies to not just real-time audio, and hopefully that gives you a better understanding of operating systems in the complex systems that modern PCs are. So memory is not real, memory is virtual, and the only thing you can touch in your program is virtual memory. And we can validate this, so hopefully that's big enough. So in this very simple program, I malloc 10 gigs, and that takes like no time. I haven't timed it, but you will see it's extremely quick. And I get a pointer back, and that's all good. And if you look at the output of top, somehow I have only 8 gigs of RAM on this machine, and it says that I'm only using 2.5 gigs. Like, what's up? I've just asked for 10 gigs. Do you mean you haven't really given me my 10 gigs? And so if you look at the top output, we have 10 gigs of virtual memory, but we're only like 600 bytes of resident memory, and that's the actual memory. So actually what happens when you ask for memory, your operating system will say, yeah, sure, you can have all that memory. And what you're being given is virtual memory. And when you actually write to this memory, that's when the operating system is going to have to map this virtual memory to physical memory. And that only happens on write. And that could take ages if your system is out of RAM. So what I'm saying here is, if you don't allocate on the audio thread, and you allocate large buffers, when you get to actually use this memory for the first time, write to it on the audio thread, if your system is out of memory, your operating system might have to take another program that's currently not being scheduled on the CPU, take its memory, write this all to disk, so that's what we call swapping, and then we'll be able to map virtual memory into the actual physical RAM for your program. And if you're out of memory and your machine is using a spinning hard drive, that could take ages, even though you haven't done any memory allocations on the audio thread. So I think that's not really a problem we have in the audio industry, because we will pre-allocate everything and we'll tend to touch all that memory anyways, maybe on the first audio callback. So maybe the first audio callback might take a bit of time for this memory mapping to happen, but then everything will be fine. Unless you have a more specific application where you're reserving a lot of memory, maybe like you need a buffer for like a long reverb tail or something. And at the beginning of your processing, you have a short reverb tail, and then later on the user gets to, like crank out that tail length. And that's when you start touching this memory for the first time. That could take a while. So there's quite a few things we can do on Linux to avoid that pitfall. So first, when you allocate, we want to never give back memory to the kernel. So what this means is when you use new or malloc, that's a libc call, and libc will usually have some allocated memory that it asks from the kernel already, and so your heap is already pre-allocated, so you're not asking for any memory from the kernel. But sometimes when you free some memory, if you had a large amounts of memory that were allocated, this might be given back to the kernel, and we don't want to do that. So if you do this, all the memory that your program uses allocates on the heap. It will never be given back to the kernel, even if you free it. Do not use mmap for large allocations. So similar to this, if you do like a very big malloc, it won't actually come from the heap most times. libc will ask the kernel for a specific chunk of memory for this large allocation. And there's a threshold above which you use this mechanism instead of using the regular heap. And if we set this threshold to 0, we'll always use the memory from the heap, which libc has already asked from the kernel before. So we avoid this trap. So the next thing is to have a single arena for malloc requests. And I encourage you to look in the documentation if you're interested in all of this. And the beauty about Linux is you can actually read the source code as well if you really want to understand what's happening. But basically, arenas are memory regions which are used for the heap. And if you have multiple of them, you run into the risk of running into the problems that I mentioned earlier. If we have a single one, the downside is malloc. There might be contention if multiple threads are trying to malloc at the same time. As audio programmers, we don't malloc on the audio thread, so that shouldn't be a problem. And then this is an amazing syscall that you need to call before, where all the virtual memory that was mapped to physical memory, we are telling the kernel, never page this to disk. So if you do this, you will never be swapped to disk. And the next two things is, so about the first thing I talked about, which is the memory mapping happens on write. And we do this, we call this pre-faulting the heap. So just touch all the heaps. So you malloc a big chunk and you just touch all of it. That will force the kernel to actually map this to physical memory. And with all the options we've set before, then we're guaranteed this is actually RAM and not just virtual memory that happens to not exist anymore. And something that's also important is when we use our stack, we don't think of memory allocations, but actually this might also cause this page fault, virtual memory to physical memory mapping. So pre-fault your stack to make sure a stack variable is not going to, if you have a large stack variable, it's not going to trigger a page fault. You need to do this for all threads. Remember, each thread has its own stack. So that's about memory. So now we're going to talk about the schedulers and how to guarantee that our real-time audio application has all the time it wants to run on the CPU and is not interrupted by something like a SSH server or whatever. So we want to make sure our app has the highest priority because the audio processing is the highest priority. So in the Linux scheduler, by default, Linux is a general purpose operating system. So the purpose of Linux is to work the best possible for the widest range of applications possible. And for this, they use what's called completely fair scheduling. So basically, there is no priority between applications by default. And the scheduler will allocate time slices to applications in a consistent way. There is, however, something called the nice value, which ranges from -20 to +20. If you're less nice, you're telling the scheduler, I really need that CPU, please give it to me. So for example, if you're an SSH server, you might want to be not nice so that if your server is really having trouble because your web server is busy serving way too many requests, as an admin, you can still log into it via SSH and see what's happening and give a chance for your SSH server to run. So that's what it's typically used for. And then we run into real-time scheduling. And here we have three options. Sched FIFO, so first in, first out, with a real-time priority. So in this scheduler mode, it's, as it sounds like, higher priority tasks get to run when they want to run, and lower priority tasks will not run until the higher priority tasks are done. If you have two tasks at the same real-time priority, depending on the first one will start, and once it's done, the next one will run. Real-time priority in Linux is expressed in a number from 0 to 99, 99 being the highest. Then we've got round robin, which is basically the same thing, but if you have two tasks at the same real-time priority, they will interleave. Typically, in audio, that's not something we care about because you pay a penalty of all those context switches. But if your task produces some meaningful output as it's running, for example, I don't know, like a scientific computation that's going to take ages, but you can plot intermediate output as it's progressing, that might be interesting, although I'm not sure why you would use real-time scheduling for such an application. And then you've got sched deadline, which is quite strange, where you say, I would need this task to be done by this specific time point. And I haven't really played with this, so I can't really tell you more about it, but it exists. So I guess now is also the time to give you a disclaimer. We've been working on this for the past 4 or 5 years. I knew nothing about Linux RT before, and this is what I know, what we have explored. And obviously the subject is extremely, extremely wide and vast. So this is an encouragement to explore. So the POSIX syscalls to set real-time priorities are pthread, set sched param, and set priority. So one of them is for the thread, one for them is for the whole process. You can look up the documentation. There's nothing complex there. Common pitfall. So because Linux is a general operating system, when you have real-time priority, you will not be interrupted until you're done. So that means if you write an infinite loop running with the highest real-time priority, your system will lock up and you have no way of interrupting it. No way. And apparently Linus Torvalds was hit by this, by a faulty real-time program, and he was really not happy about this because for him, the system should never lock up. And so the kernel has this runtime parameter, which is called a schedRT runtime US, which is basically a maximum proportion of time that can be used by real-time tasks. And so it's typically computed over a period of, I think it's 1 millisecond. So you can look up that second line will show you what the period is. And then you say how many microseconds in that period can be allocated to real-time task. It's terrible because it's computed over a fairly long period of time. So that means if your RT task have a lot of work to do for 10 milliseconds, this will interrupt them, which you probably don't want. So you need to disable this, and you need to disable this at every boot with the sysctl call that's in here. And then make sure your real-time tasks don't block, don't have any infinite loops. But if they do, you probably have a bigger failure, and at that point, you can probably just unplug the machine anyways. because your app has failed. So a quick note about priority inversion, because now that we talk about real-time priority, I think that's an important concept to mention. So this example is on a single CPU system, and obviously things would be slightly different on a multi-CPU system because the scheduler has more space to work with, essentially. So imagine we have a first task, and it's running at a fairly low priority, and it's running. At some point, it takes a lock. Then we have a second task that needs to be scheduled, and it's a higher priority. So it will, at this point, what happens is we have what's called preemption. So task 1 still has some work to do, but it's preempted. The CPU is preempted, and task 2 gets to run. So until now, that's what we want. That's what we expect. And then same thing, we have another higher priority task. Let's call it task 3, and it runs. And at that time, task 3 wants the lock that task 1 got. So what will happen is at that point, that thread cannot go any further because it needs that lock to be released. So the scheduler will put the thread to sleep, which means task 2 gets to run now. Task 1 still doesn't get to run because task 2 is higher priority. And at some point, task 2 is done, so task 1 finally gets to run. Task 3 is still sleeping, still waiting for that lock. At some point, it releases that lock, and then task 3 can get that lock. Task 1 gets preempted, and task 3 gets to run complete. And once it's complete, task 1 gets to finish. So this is what we call priority inversion, where we have this high priority task 3, had to wait for a lower priority task 2, to finish. Obviously, there is this lock. So task 1 is lower priority, but by grabbing this lock, we're kind of accepting this. But that's not great. So the solution to this is what's called, do you see my cursor? Yeah, you see my cursor. Priority inheritance. So when task 3 wants to get that lock, the kernel will see that this lock is currently held by task 1, and task 1 will inherit the priority of task 3. So task 1 will be boosted until it releases that lock, and as soon as it releases it, task 3 gets to run. And then we have the nice waterfall that we would expect, where the highest priority task is always running. So if you're doing multi-threaded processing and you're using some kind of synchronization to wake up background threads, it's very important that you use mutexes, because mutexes can only be held by a single thread, which allows the kernel to keep track of this, the priority of which thread holds a given lock at any time. It doesn't work with semaphores, because semaphores, with this resource counter pattern, multiple people can hold a semaphore at a given time. So when you use mutexes, POSIX mutex, this doesn't happen by default, so you need to use this prior inherit option, and that's what it looks like. Okay, so now that we know a little bit more about scheduling, we want to monitor what's happening to make sure that any tweaks we make are working as intended. So Linux has this amazing tool called trace command, and that uses kernel tracing features which are deeply rooted into the kernel. And so with this command, we're going to look at what are called sched switch events. So a sched switch is when what thread is running on the CPU changes, and sched wake up events. So sched wake up is when we're asking a thread to wake up, for example, by releasing a log or a condition variable. And so there's this other great tool called kernel shark, and that's what it's going to look like. So I've got a little video here. So I have a trace here. So that's actual data from our product. And you can see, you can zoom in. So it's a multi-core system, so each line represents a core. And you can look at the sched switch events, and you can see there's a bunch of sched wake up events, and then we can see the threads waking up. And you can see they don't all wake up at the same time. There is a penalty to waking up a thread. There's going to be a latency here, and we're going to talk about this a long time. And here we're looking at when this was unzoomed, we were looking at a bunch of audio callbacks, and we could see them executing. Here we're looking at 2 audio callbacks. We can see there's a lot of margin between the two, so we are meeting our deadline in this case. So the problem with kernel shark is I don't really like the UI. Like it colors the threads randomly, which is kind of annoying. So what you can do instead is generate a report from this trace. So that's what it's going to look like. So you have the CPU core of the event, and then you've got some information about the event. So you see some wake up events, and it's telling you what thread is trying to wake up, and then you've got a switch, which tells you which thread was running and which thread is now running, and you have the real-time priorities that are there as well. And then you can do a little bit of post-processing on this to graph it with your library of choice. Also, there are a lot of events on my system. I've got more than 1,500 possible events. So list them, and there will be interesting things to see. So maybe you're doing some networking, maybe you're doing some I/O. This can give you a lot of insight as to what the kernel is doing. So with a bit of post-processing, I'm using this Chrome tracing tool. So because I guess developing web browser is also a complex task, so they have their built-in tracing tool to analyze the performance of Chrome, but the format they're using to display this data is open and anyone can use it. It's a JSON file. And so that's what it looks like in Chrome tracing. And what's nice is I can always color the same task in the same way. And it's very easy to measure how long some tasks take. So here I'm measuring some stuff. I can look, okay, I can see my whole audio callback is taking about 800 microseconds. Our block size is 1.3 microseconds, so we have some margin here. I can see that Jack, which is the audio server we're using on our system between the ARSA layer and our application layer, I can see that this is a 28 microsecond overhead. So in our case, it's fine, it's not much, but I can see exactly how long that takes. Even though I didn't write that program, I don't need to time it, so that's great. And then, oh, I guess that's the same video, sorry. So what would be good then is also to look at what's actually happening in your program. And that's a little bit harder, but what you can do is generate events that are in the same event log as all those kernel events when your program hits a certain point. So when the instruction pointer hits a certain point. So it's a bit of a pain. So that's what it looks like. So you need to create this probe event. So that's the name of your probe. You need to give it the path of your executable, and you need to give it the address of the instruction. Obviously, finding this out is a bit of a pain. But what you can do is, so that's how we do it. So we put some comments in our code saying, okay, I want a probe, I want an event when I hit this line here. So that's the syntax we're using. We're finding all of those with grep in our sources. And then what I do is I use a GDB script to put a breakpoint on this line. And GDB will tell you the address of that breakpoint, and then I can use this to generate this script that you can see here. So I can put the address in here, and that's the name of those two events here. And then, so if we look at this again in our Chrome tracing, you can see these little orange blips here, which are my custom events. And what's great is it's in the same log as all the other events. So if you have a lot of single-threaded work and the multi-threaded task doesn't tell you much, you can see exactly when you're hitting stuff. And this is a very good complement of micro benchmarking. So there was this great talk yesterday about CPU pipelines and how you could execute 2 bytequads for the price of 1 if you interleave them. So that's your micro benchmark. Once you actually apply it, you could have some events every time you're processing some bytequads, and you could see if you actually see the gains in real life. So let's look at some data of what it would look like if you were to start this journey from scratch on an existing audio application. So that's a vanilla multi-threaded audio application. So we're not using real-time priorities. And that's what it looks like. So you can see there's a lot of gaps in all my tasks, which is not great. But this callback took 920 microseconds. As I said, we have 1.3 milliseconds to do it, so looks fine. But if we zoom out, we can see like this. We have all our callbacks running, and here, ooh, that's a glitch. And we've got this network CTL task running. So I don't know what it is. Well, I guess it has something to do with network, and it's a Linux system. It must be doing some networking stuff. So that's not great. And so if we zoom here, we can see like we have our binaural processing, which is multi-threaded, which is running here. And for some reason, the scheduler was like, you know what, the network stuff needs to run, probably because network's important, and scheduler has no clue that our app is important at this stage. So this network task gets to run like for a long, long time, and then at some point it's done, and our binaural, that poor binaural thread gets to finish, and then the rest of our audio application can run. And here, that's when we return the audio buffers to our audio server. You can see Jack running here. So that was interrupted by this task. So the next step is to add some real-time priority. So it's quite simple. We're just adding, we're setting all our threads to use the sched FIFO scheduling mode. And we put them all at the same priority because anyways, like there's some data dependency between those threads. They're woken up. And so that's what it looks like now. So you can see it's a lot more compact. And we can see like some housekeeping tasks that are done by the system. There's this stuff here, which is running here. Then it gets interrupted by audio. Then it gets to resume. It's interrupting by audio again. And then it gets to resume. There's this green one here as well. We can see it running here. It's interrupted by audio. Then it's running here. So that's what we want, and that's great. So if we look, there are still one thing that might be important is you can see this main audio thread here, the blue one, is jumping around from one CPU core to another. And it's a multi-threaded system. By default, the scheduler will try to use all the cores as efficiently as possible. And this might mean that from one callback to another, a task might jump CPU. Actually, a task might even jump CPU even before it's done. And there's a penalty to this because our level 1 cache are local to the CPU core. So when you move a task from one core to another, well, you lose all your cache data, essentially. So we can force the scheduler to not do this using a feature called CPU affinity. So we can pin processes or threads to a set of CPUs. So you can either give it a list of cores it's allowed to run on, or just a single core, and then it will always be on that core. There's also something interesting to mention here. There's a kernel boot parameter called isol CPUs. And basically, if you can tell Linux, this core, you leave it alone by default, you don't put anything on that core. And that can be super useful if, for example, you have like a dual core ARM, your audio processing is single threaded, you can isolate one core, and you're guaranteed that Linux will never put anything on that core, ever. So then you need to manually use this set affinity call to put your task on that core, otherwise it won't be there. And so that's what it looks like once we do all this. So you see it's neat and tidy. We can see all our fairly heavy multi-threaded tasks get to run. We can measure all that overhead of starting and joining our threads. So we are using a static load balancing. So when a thread starts, it knows all the tasks it has to do. Obviously, that means some tasks will take longer than others. So for example, when that thread is done here, this thread still has a lot of work to do. Maybe it has multiple tasks to do, but that thread doesn't get to help. That's our current strategy. It works for us. There are other ways of doing this. But we can see all that stuff. That's the main point. We can see how our application behaves. And if we change our strategy to our multi-threading, we can dig very deep into what's happening on the system. So then the next step is to do long-term testing. So this graph, what it shows is basically the red line is the time it takes to execute our audio callback. So we just run the app for multiple hours, and we do this on our CI every night. And so this is instrumentation that we have built into our app, and we just time, just using STD chrono, simple stuff, the time it takes to execute our audio callback. And then we can be guaranteed, we can at least know if there's a probability that something goes wrong over a long period of time. And so if we look at this, that's great. So here, because it's a lot of data, we aggregate, so we keep the average and the max for, I think, 10 samples. So our audio blocks being 1 millisecond, so 10 samples is 10 milliseconds worth of data. So you can see the max is quite a bit higher than the average, and that's because of the scheduling latency that we're going to talk about. There's still a level of unpredictability, and basically that's this gap between the two lines, the difference between the average and the max. But we really only care about the max. And so in that case, we're good. So let's stress test it, right? So what we're doing here is we're running a stress ng, which is a stress tool. And I'm running 12 instances on my 12 CPU system. What you can see is actually the Linux scheduler is not putting it on the first core, which is normal because we've isolated it. But for some reason, it's also not putting it on this core here. I'm not sure why. So another reason to control CPU affinity is you might have n cores, create n threads, and for some reason, Linux might decide to put 2 of those tasks on the same core and leave 1 core alone. So far, it looks good when we see like this. So we see our audio processing, and we have our stress tool, and our audio processing gets to interrupt our stressing tool. So that's fine. So let's look at the long-term test now. Ooh, that's pretty bad. So the dashed red line is what we had previously before we were stress testing. So if we look back at our graph, actually what's happening is every time this stress test tool gets to run in all our little gaps in our multi-threaded processing, it's going to destroy our caches. And this slows things down a lot for us. And the problem is there is no easy way of preventing this. With real-time priority, you run when you have work to do, but when you don't have work to do, other things get to run. And so the hack, and I'm being very honest about it, the hack we found for this is to run some no-ops. So we've got these CPU hogs threads, which we start at the beginning of our audio callback and stop at the end of our audio callback. And they're just executing no-ops. And they also run with real-time priority, lower than our audio processing. So the scheduler will automatically interleave them in all the gaps. And that pushes the stress test out of our audio callback, and it prevents all those all this cache thrashing that we're seeing. So we're burning a bit of CPU. We're using an Intel intrinsic, like a pause instruction where the CPU is basically doing no ops, and it's quite energy efficient, so it's fine to run this in the loop. And so if we look at the long-term test, so that's stress testing before adding those no ops. That's after, so it's quite a bit better. But that was before doing any stress. So you can see where the max is hovering about 1,000 microseconds with the stress test and this hack. Before it was quite a bit lower. So there's still a cost. And so the point I'm making here is real-time priority seems awesome the first time you see it, but it's not magical, and you still need to be aware of what's running on your system. And luckily, if you're doing embedded, you know what's running on your system. But Linux is complex. Linux distributions are large. There's this network CTL task. I guess it's doing some stuff to the network with the network. It's probably important. We need the network, but I'm not sure what it does. If I wanted to know the code that's actually executed and know what it's actually doing, I would have to dig fairly deeply, and we don't really have time to look for all these things. So let's try a different stress. So same tool, stress ng, but I'm using the memthrash CPU stressor. So far, so good. We have our no ops that are preventing it to run at the wrong time. So it's running only in between our callbacks. So it looks good. So this is what we were seeing when we were using the CPU, so the previous stress test mode. So about 970 microseconds for audio callback. With memtrash, it takes more than twice the time. Ouch. And if we look just at the beginning, So just the beginning when Jack gets to run. So at this time, our thread, we're not even in our audio code yet. We're in the audio server code. So we don't even know, we have some work to do yet. And then so that's, we use Juice for audio, by the way. So that's the Juice audio callback, and Juice does some stuff before it gets to our code. And you can see when our first multi-threaded task gets to run here. So that took 120 microseconds with the cache being destroyed with this memory stressor. That took 30 microseconds. So basically, be aware that modern CPUs are much faster than the memory. They rely heavily on caches to be fed and be able to execute stuff. If your caches get destroyed, your performance is going to be destroyed by, here it's only a factor of 2. For some algorithms, it can be a factor of 10 easily. So I know, for example, in high-frequency trading, they keep touching the data all the time to keep the cache hot. So there are other techniques to mitigate this, but sadly there is no perfect technique like real-time priority, which is a very hard constraint on the scheduler. We can't tell the CPU to keep this specific memory region in cache at all times. There's no way of doing this. It's the CPU doing its magic, and we can't control it. One more trap. So this is a 4-hour test, and that's how it looked like. So for some reason, it was looking fairly good, and we've got these weird bumps that take a while. And when we were looking at the scheduler, we had these weird gaps, which are also quite weird because these threads have some work to do. So, but for some reason they get interrupted, and we didn't really know why. That turned out to be due to Intel C states. So again, CPU are very complex. C states are power-saving modes, and your CPU will automatically, when some parts of the CPU are not in use, will turn those parts off. And when they need to be turned back on, this takes time. And there are super opaque heuristics as to know when the CPU is going into those C states. So the deeper you go, the higher the latency to run back up to full speed. So power consumption and thermals are the main 2 metrics that the CPU is using to decide in what power state it's on. And you don't really control those. So the fix for us was to just disable them. So you can disable them either in the BIOS or you can compile a custom kernel with this stuff disabled, and that will solve your problem. So the funny thing is, all I've talked about so far, this applies to regular Linux. And this talk is about Linux RT. So what is actually Linux RT? So if you use this uname command, you can see what kernel you're running. And that's what it would look like on a vanilla Debian. So you have your kernel version here. And so the important thing is the kernel version, it's the version of the sources, and the kernel has hundreds, even like actually thousands of configuration options when you compile it. So the version actually tells you nothing about what you're running. Most distributions will come with a precompiled kernel, I guess all of them. So we're running the Debian kernel, and that's the version number that Debian put on it. So that tells you what configuration options they've enabled or disabled. And they probably also patched some sources for some reason because they needed some hardware support that's not supported in this version of the kernel. Maybe they patched some security issues. So important thing to know is your version number of your kernel tells you basically nothing about your kernel. And that's what it looks like on our device. So you can see we're running 419 as well, but it's our custom version, and we see this preempt RT. So what this means is that we have the preempt RT patch. So that's maintained by a nice set of guys. Here's their Wikipedia page. So preempt RT is a patch you need to apply to kernel sources. And then once you've applied this patch, when you get to configure the kernel, you'll have an additional option, which is preempt RT, that you need to enable. Some distributions have pre-built preempt RT kernel is available. Debian has one, so you can swap to the RT kernel by just installing a Debian package. We have a custom version for this C state issue that I mentioned. We wanted them to be disabled in the kernel. Okay, but what does it do? So it does two things, and these two things are here to make sure the scheduler behavior is as predictable as possible. So the kernel has to do a lot of stuff, and the kernel has to deal with a lot of tasks. So the kernel is full of locks, right? There's a lot of things that only one application can do at the time. And those locks are spin locks because spin locks are very efficient. But the problem with spin locks is, well, they spin and you don't know for how long they're going to spin. And the operations that are protected by those spin locks are pretty short. But what this means is when you're in those spin locks, you don't get a chance to interrupt the task that's currently blocking it, or the task that's waiting for that lock. So all the spin locks are replaced by real-time mutexes. So that's a big change. Like we're telling all the locks in the kernel are replaced from spin locks to RT mutexes. And the other thing it does is interrupt handlers are placed on their own threads. So interrupt handlers is how hardware talks to the kernel. So maybe you have a sound card, USB sound card. Well, actually, I think USB uses point. You have a PCI sound card, and it's using DMA, so direct memory access, to write the buffers directly into the RAM of your machine. And then at some point, you'll get an interrupt from the sound card to tell you, okay, those buffers are ready to be read, and that's what wakes up your audio driver and then your audio application, and that's when you start processing your samples. And those interrupt handlers, they are executed in the context of whatever task is currently running. So if you look at the scheduling graph, you won't see them happen. So it will just interrupt whatever's running. They have got the highest priority, and they will do whatever they do. And what they do is implemented in the drivers. And some drivers might be very good at just setting up a few flags and then going back to sleep, so doing very little work in the interrupt handlers. Some drivers might be very bad, and you don't know what you have on your system. Maybe this network adapters driver is written well, maybe this network adapters driver is written bad. And while you're receiving too much network traffic, then you've got all these interrupts that are preventing your high priority tasks from running. So the RT patch places those interrupt handlers into their own threads. They run by default with the RT priority, and you can bump the priority of your application above those. So basically, it's about reducing all the things that could be running and interrupting our application. What this means is average performance actually decreases, but predictability increases. And I'll try to finish very quickly. So as I said, preemptibility is key to making sure high priority tasks can run when needed. So this means user space tasks can have higher priority than interrupt handlers. So here's an example. Here I'm talking to like a low speed peripheral on I2C bus. And obviously our PC is a lot faster, can spit out data a lot faster than this I2C bus. So what's happening is we're sending some data, and then at some point, very quickly, the device is like, hang on, I'm sending this like only a few bytes at a time. You need to wait because my buffer is full. And then when this is sent onto the wire, you get an interrupt. And then your driver can send more data. And so you can see like this is super inefficient communication. So you see all this like ping-ponging of this task trying to send data and being constantly interrupted because that I2C chip buffer is full. And then you get that interrupt. So all those interrupts, if we weren't using the RT kernel, they would be interrupting our audio application and we wouldn't even see it. So that's an example of that. And then to check your kernel performance, you can use this cyclic test, which basically will set up a hardware timer to wake up a thread at specific intervals, and then it will measure when the thread actually gets woken up compared to when it should be woken up. And that measures scheduling latency. So if I have some work to do now, when do I actually get on the CPU? And we want this time to be as low as possible. And you set here with this -P60 the priority of that thread, because obviously if that thread is low priority, then it might not get to run because something else might be running. So it measures the scheduling latency at a specific priority level. So that's what it looks like. So you can see you've got some average numbers That's in microseconds. And the max numbers. So you need to let this run for a while, right? Because we're interested in long-term performance. And these are the results you would get. So on a regular kernel, 3 different priority levels. You can see the averages are very low. We're in the microsecond range. So waking up a thread is actually on average very, very cheap. But you can see sometimes it can take a long time. So at priority 40, almost 400 microseconds, when I go up the priority, this decreases a bit, so I guess I'm getting above some lower priority tasks. But that number is due to those interrupt handlers or the spin locks in the kernel, which are preventing my task from being scheduled when I want it to be scheduled. And this, I mean, like 240 microseconds, that's a huge number, right? We have 1,200 microseconds to process our audio. If we wake up a thread and it's delayed by 250 microseconds, it's a massive deal. And with the RT kernel, you can see that the average numbers go up because the kernel is less efficient. And then at different priority levels, you will see different numbers, and you can see at the highest real-time priority, I'm in the 50 microseconds range. And so that's basically the gap that you saw between that blue line and that red line. On average, we're in the 6-7 microseconds range, but sometimes it takes more. And that really depends on your system, on your driver, on your hardware, your CPU, what's running on your system. So you need to measure this for yourself. But this is what the RT patch does for you. And it's key to unlocking this real-time performance. Like the real-time priority itself is not enough. Okay, I think we're already over, but it's the break. So I'm happy to take a few questions. Sorry for going over.